All right, so let me do this and the next four questions as a group. These are all from chapter 5, hopefully relatively simple application of Newton's second law questions. And I think I explained this before. I'm kind of going back and backfilling some of the homework help videos that didn't exist because I added a bunch of new questions. Through like chapters 2 through 5 that someone else had programmed in. I thought, hey, these look like good questions. Let me give more practice to that people can do. So I'm doing all these homework couple videos in case people are having difficulty with the questions. Also, this would be my opportunity to test and make sure the questions don't have errors in it. So let me do this question and the next four group of questions, and I'll try to do them relatively quickly because again they ought to be easy questions. So let me start. This question says, suppose two children push horizontally but in exactly opposite directions. Okay, I think I'm gonna start drawing free body diagram just to help me sketch out this scenario. So there's a third child that's in a wagon, and it's describing two horizontal forces. The first child exerts a force of 63 Newton. Let's say it's to the right. The second exerts a force of 100 Newton. Okay, let's say it's to the left. And there are other forces. Friction is 13 Newton. Now the question doesn't tell us the direction of the force, but it's quite easy to, or common, to assume that things are starting from zero speed, then the net force gives you the direction of acceleration. So with the arrangement of forces like this, acceleration is probably leftward. So with those assumptions, I'm going to say friction is to the right. So friction of 13 Newton. And it says the mass of the third child, third plus wagon has a mass of 23 kilograms. So that's everything diagrammed in. So the question is asking for acceleration. So I should first calculate the net force. I'm using Newton's second law. Newton's second law says net force is equal to mass times acceleration, or inverting the relationship, acceleration is net force divided by mass. So I'm gonna calculate the net force first, and then I'll divide the mass. So net force, it looks like they're not really, they don't care about the direction, so I'll make leftward direction be positive. So it's gonna be 100 Newton minus 63 Newton minus friction going in the direction that I guessed would go, 13. That's the net force divided by the mass, 23 kilogram. I can't do that in my head to 1% precision. It should be 1.04 meter per second squared. And this time I just decided not to put in any units. It's a choice that you can make, and you have to stick with one or the other. Either no units on any of the numbers and just stick with the basic SI units, or put units in every single number. There's no in between, one or the other. So okay, good. That's correct. What would be what would the acceleration be if friction were 37 Newton? This is one of the reasons I like using Wolfram Alpha. It's a lot easier to make modifications to your input, unlike if you are using. Oh, I guess that must have been set up to give you 0. Unlike if it's a calculator, then I have to re-enter everything. Wolfram Alpha, I can just make a simple edit and do that. Yeah. All right, that's the first question. Let me go to the next question. Okay, this is problem 33, same chapter. It says a powerful motorcycle. Let me just erase all the writing and get back to home screen of Wolfram Alpha. A powerful motorcycle can produce an acceleration something while traveling at some speed. At the speed, force. Okay. So let me just sketch the picture just so I can make sure I have correct mental image. So I have a motorcycle I don't know how to draw a motorcycle. That's my motorcycle. It's traveling with some speed, and it's producing some. It's undergoing some acceleration under some motor and whatever. And at that speed, the forces. So this is where I want to draw a free body diagram to make sure I understand the forces on the motorcycle. There are forces resisting motion, friction and air resistance. So those forces should be leftward as drawn, given as 440 Newton. Air resistance analogous air friction. Okay, opposes motion or not. Unless it's wind. Yeah. You can always come up with the counter examples, I think. But let me not get distracted by that. What is the magnitude of the force that motorcycle exerts backward on the ground? So to understand the wording of this question, motorcycle exerts backward on the ground to produce its acceleration. So for the motorcycle to be accelerating forward, there must be a net force forward in the forward, rightward direction. So there must be some kind of F forward. And it comes down to the question of how is this forward force generated? And ultimately, it's the force between the motorcycle tire and the road. This contact of surface is how that force is being exerted on the motorcycle. And in order to have that force appear, what the motorcycle does is, it tries to spin this wheel. And in trying to spin this wheel, that's when it exerts a force on the ground. So if I draw a free body diagram of the ground, there's actually a backward force on the ground. And this is the Newton's third law pair, the action force and the reaction force. So I might label this as F forward, because by Newton's third law, the magnitude of this force has to be equal to the magnitude of the forward force on the motorcycle. So the question is asking for the magnitude of the force that the motorcycle exerts backward on the ground. So it's asking for magnitude of this force. I can find that basically by finding this force here, because magnitude will be the same through Newton's third law. So I think I have all the information. Now here's a weird thing. The question asks for the net force. So let me go through the steps I was going to go through before I got confused by the net label. So where I would start is with the statement of Newton's second law. That'll show me what gaps there are for me to fill in, if any. So I say net force. Oh wait, that's double. The summation implies net. Net force is equal to, so I have the forward force, which is what I actually want, minus all the frictional forces, the 440 Newton. 440 Newton, and that should be, through Newton's second law, equal to mass times acceleration. And I think I am given the acceleration, I am given the mass, that's what I was using just now. So I think I have everything. I can just solve for the forward force here. It's so even though they gave us the speed, I don't think I need it. So I'll just ignore it. Sometimes, we give you extra information to basically confuse you. Sometimes people just randomly combine numbers to try to guess at an answer. So let me solve for forward force. So the forward force is equal to mass times acceleration. I can plug in the numbers, plus 440 Newton. Yeah, and since everything is in basic SI units, let me again not put in any units. So I already have mass 245 kilogram times the acceleration 2.5 meter per second squared, plus the backward force I have to compensate for 40 Newton. So it should be now 1052.5 Newton. 1052. Or I should be able to round it to 1050. Yeah, let's see. Good. Yeah, and it's also not a net force on the ground, because there are other things interacting with the ground, so it doesn't make sense as the net force on the ground. But yeah, so That's the force. And even though this is not technically what the question is asking, again, through Newton's third law, what I calculated here has the same magnitude as what the question actually asks. Okay, let's go to the next question. Oh, I have to jump a little bit for that. Okay, this is the next question, problem 35. It says a driver applies the brakes when the car is... let me just start sketching. The sketching that I'm doing right now, it's kind of a doodle. It's, I guess, not strictly necessary, but it's a habit I've built. I kind of need to draw out things to make sure I don't feel like I'm missing out any information. So you have a car, it's moving at some speed, let me call it V0, and there's a brake being applied, and the car comes to rest after traveling. Okay, it's describing some distance it's traveled before coming to rest, delta x. So there must be an acceleration backward while it's coming to a stop. What is the net force on the car during its acceleration opposite to the motion? Yeah. So again, simple application of Newton's second law. Net force, which is what they're asking, is equal to mass times acceleration. So they've given you the mass, so really all you have to find is the acceleration, then you just multiply that to mass and you're done. Again, you don't need the speed that they gave you. Or actually, sorry, I misspoke. This time you actually do need the speed. Because here the way you are going to find the acceleration is through kinematics. And I kind of, with all the given information on screen, I kind of think through the kinematics formulas in my head. And here the main thing that gives me biggest hint is that there's no time information given. So I'm thinking of the kinematics formulas that don't involve time. And I do remember one, the V squared formula. V final squared is equal to V initial squared plus 2 times acceleration times delta x. And remember, these are kind of like vector quantities. So when the displacement and the acceleration are in opposite directions, you need to make sure this ends up being negative. So this formula, I think, has everything I need. And it has the acceleration that I'm trying to solve for. So let me solve it for acceleration. Solving it for acceleration. Just going to do the algebra in my head in the interest of time. Double check. V final squared minus V initial squared divided by 2 times delta x. And I guess, yeah, so I'm gonna, let me plug in the numbers. I'll get a negative number for acceleration, and I'll just ignore the negative sign and just answer with a positive number here, because I think that's what they're asking, looking for. So here, V final squared is 0, because it's coming to 0, rest at the end, minus V initial squared. Let me leave that as symbol here, and I'll plug in the number into Wolfram alpha with the units this time, so that Wolfram alpha does the kilometers per hour conversion for me. Kilometers per hour, it's not SI units, it's not meters per second. That divided by 2 times delta x. So once I have this, then all I have to do is multiply the thing with the mass. That'll give me the number I'm looking for, net force. So I'll do the rest in Wolfram alpha. So 0 minus the V initial, 86 kilometer per hour squared, divided by 2 times delta x, 42 meters. Now that I'm putting in unit for one of the quantities, to let Wolfram alpha do the unit conversion, I have to put in the unit for everything. That times the mass, 1000 kilogram. So that should give me something in newtons, and I'll ignore the minus sign because I don't think it's looking for a signed answer, but we'll see. So it should be 6794 newtons, or rounding to 3 significant figures, 6790 newtons. You don't have, I mean, I like rounding to 3 sig figs. So it says it's wrong. Okay, maybe they do literally meant this, the vector symbol. Maybe. So, alright, let me put in a minus sign. Let's hope it grades that as correct. Okay, I guess they did actually mean it for to be signed the quantity. This is why you have a practically unlimited attempts. So sometimes it's I don't know. I thought it was unclear in the question if I should put a minus sign or not. But try both. All right, let me get to the next question. Okay, so this is the next question. Problem 36. On some mass passenger in an SUV traveling at some speed, wearing seatbelt. Driver slams on the brakes. Oh, wait. It feels like it's the exact same question that I just did. It's someone slowing down. I got initial speed, coming to a stop. I got distance. Let me just change the numbers here. So my initial speed was 104 kilometers per hour. And I'm basically reusing this whole thing. 2 times the distance is now 41 meters. Yeah, that's more than 1%. So if I don't change it, it will be great. That's incorrect. The mass is 80 kilograms. So force of the seatbelt on the passenger. Yeah, I think that should be right. So we are assuming the seatbelt is the main thing that's exerting the backward force on the passenger. Under that assumption, the answer ought to be, and I guess I'm gonna assume it wants a minus sign, so minus 814. Let me keep all four sig figs. Minus 814.2 newtons. Probably. Yeah, good. I'm glad I didn't erase any of those because I didn't read the questions ahead of time all that carefully. Okay, I got the next question, and I think that's the last one. Let me get to that question. Okay, question 37. It says a particle of, okay, now it's a different question. Let me just reset everything so that I can just sketch things from scratch. Particle of some mass. Let me just draw a representation of that mass or particle, a dot. It's acted on by a force, and let me indicate the direction. The I hat, that's the y, same as y hat. So I'm gonna say force is in this direction with my x and y axis. Define the normal way. So this should be my applied force in the I hat or y hat direction. What is the particle's acceleration? They put this absolute value, so they just want the magnitude. 17 divided by 3. So I think I can do that in my head. That should be 5 point. So the equation I'm using, just to spell it out, is Newton's second law. Net force is equal to mass times acceleration. Here they gave us just the net force or single force. That is the net force. So the acceleration is the net force divided by mass. So I'm just doing that division in my head. 17 divided by 3, so 5.20, so 6.66, repeating, so round it to 7 at some point. That should be correct. Let me just double check. Okay, if the particle is at rest, how far does it travel? I think it means particles, oh yeah, starts at rest, sorry, I misread. Starts at rest, how far does it travel in the first 5 seconds? So again, this is now a kinematics question with a given acceleration, and I'm in my head, I'm kind of flipping through the kinematics equations I have in my head. And what I'm remembering is I'm given the initial speed, and I'm given the time, unusual, I think, and I'm given the acceleration, or I calculated the acceleration. So I think the expression that will be most useful here is the one for the position as a function of time, which is the initial position plus the initial velocity times time plus 1/2 times acceleration times time squared. Lots of times. So for delta x, I can basically say my initial position is 0 and my initial velocity was 0, told to be starts at rest. So really my final position should be just 1/2 acceleration times time squared. So 5 squared is 20. Yeah, I can't do that in my head. All right, let me just do it in Wolfram alpha. So 1/2 or 0.5 times the acceleration. I'll put in the original expression, 17 divided by 3 times the time squared, 5 squared. So 70.83 meters. That's probably right. Yep, that's it. That's the last question in the set.